Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to have a bit of a shootout in terms of oscilloscope bandwidth, and we're going to do it by measuring the bandwidth of the scopes using the very fast rising edge of a square waveform. Now, a lot of people will say that's a much better method of measuring bandwidth than by the normal method of looking for the 3 dB down point. I'm not an expert and not sure about that, but I saw Alan Wolk, W2AEW, using a square wave oscillator to do this kind of thing. So I thought it might be useful to collect the various scopes that I've either owned or still own together and do those tests and see what we get. So let's start by having a look at the theory of it all. Okay, I'd encourage you to have a look at W2AEW's video. I'm going to put a link at the top of the screen for that, which is where I got the idea of putting the fast rising edge oscillator together. And Alan suggests that you can get an approximation of bandwidth by using the following formula: 0.35 divided by the square root of the rise time of the scope squared minus the rise time of the edge of the square wave that you're using, also squared, and the rise time will obviously be in seconds and the output will be in hertz. So an example: measured rise time on a scope, say it's 4 nanoseconds, and let's say the edge rise time is 2 nanoseconds. Putting those into the formula, then it's 0.3 divided by square root of 4 nanoseconds, that's 4 times 10 to the minus 9 squared, minus the edge of the square wave, which is 2 nanoseconds, 2 times 10 to the minus 9 squared, and the answer there would be 101.03 megahertz. The actual answer is in hertz, but just to make life easy, I've converted that to megahertz. So what we're going to do is we're actually going to do the measurements with a Schmidt trigger oscillator, and that's because we need a fast rising edge. But I'm also going to show you how you can use a signal generator as well, and I'm going to show you one of the pitfalls for that too. So the circuit we're going to use, very straightforward. This has appeared on my videos before, and this very simple circuit produces a very fast square wave output with a very fast rise time. And the chip we're going to use is one of the 74 series logic chips, but we're going to use the AC version, AC standing for Advanced CMOS, which makes it very, very quick indeed. So there is the little beastie, and I've tried to make it as efficient as possible, so I've built the entire circuit on the underside of a DIL socket, and the little red and black connections you can see there are where I'm going to attach the scope probes, so hopefully we'll get minimum amount of interference. Okay, let's now go to the bench and let's have a look at how we might measure rise time on two scopes using the signal generator. Here's the general arrangement then for checking the rise time of a square waveform. So I've got the Siglent 1032X outputting a 16 kilohertz signal, 2.5 volts peak to peak into 50 ohms, and it's a square wave. Why have I done that? Well, that's because the specification tells me here that for this particular model, 2.5 volts peak to peak into a 50 ohm load between the 10 and 90% points. The rise time of the signal generator is 3.8 nanoseconds. So here I've got the tablet Fernstein 1013 tablet scope attached, and I'll put a screen grab on to show you in a moment, but essentially the way this works is you measure the rise time 10% up from the bottom and 10% before the top. Now we can quibble about exactly where that is on here, but I've got this at its fastest time base, which is 10 nanoseconds per division, and I reckon that it crosses that division at about 10%, and I reckon it crosses that division about 90%. So that will make that measured rise time there 10 nanoseconds. So that's what we do the maths on, to do the calculation, which we'll look at on a table in a few minutes. Now I'm just going to disconnect that and pop it onto my Siglent 1104X, which I've also got set at 10 nanoseconds per division. And the nice thing about the Siglent, of course, is it will actually measure rise time for you using that 10 to 90% method. So I'm going to just clear the statistics. So it's now measuring the rise time. It's done about 100 measurements now, and I'm getting a mean of about 4.05 nanoseconds. So you can see straight away a very, very different rise time measurement on the Siglent compared to the tablet. So we'll look at what that does in terms of numbers in a moment or two. But the reason I've picked 16 kilohertz has got some logic to it, and that's because if you look at Alan Walk's video, W2AW, I'll put a link at the top of the screen there for you to go to that. He produced a Schmitt trigger oscillator using the SN74AC14, which is the advanced CMOS chip. It's quite fast. It's a very minimalistic design here, trying to keep the leads as short as possible. So I've got the chip running there with a capacitor and a resistor to give me the Schmitt trigger oscillator. And Alan is of the opinion that the rise time of this circuit is about 2 nanoseconds. So it's very fast indeed. So if we now swap from the signal, and that oscillator just happens to run at about 16 kilohertz, that's why I've picked 16 on the signal generator. So if we now pop that into the Siglent, and we'll just clear the statistics again, and we're getting a rise time there of about 3.72 nanoseconds mean, something like that. Again, we'll put these numbers into a table in a minute and talk about them. So we're saying about 3.72 nanoseconds. Let's see what the tablet scope makes of that very fast rise time. I'm going to have to just change the vertical scale because it doesn't output quite so much. And again, struggling to trigger, but you get the general idea here. If I'll just pause that so we don't have the signal jumping about. Again, we've sort of got about 10 nanoseconds, something like that. We've got about a division between the 10 and the 90% point, so it's pretty much the same. So we'll see what that does to the maths, but we know that the rise time of the Schmitt trigger oscillator compared to the signal generator is significantly different. We've got Alan Walk estimates 2 nanoseconds for that, whereas the signal generator spec here is telling me 3.8 nanoseconds. So let's now hop across to the calculations in the table and see how all this works. Having seen the practicalities using the signal generator, let's have a look at the results and see what they actually mean. So the settings then, the signal generator was set to 16 kilohertz, 2.5 volts peak to peak, into 50 ohms, and I've put the a little clip there from the specification, and the rise time of the signal generator is the very bottom line for my version, is about 3.8 nanoseconds. The display of the tablet scope looked a little bit like that, and I reckon that between 10 and 90% of that rise is about 1 division, so 10 nanoseconds. So if we plug those numbers into the calculation, 10 nanoseconds squared is the rise time of the scope, minus 3.8 nanoseconds squared, which is the rise time of the signal generator. That gives us an answer of about 37.8 megahertz. the specification for this scope is 100 megahertz, and it probably won't come as a surprise to many of you that we've got an answer of 37 megahertz. Now, we also looked at the Siglent, and the Siglent is a 100 megahertz scope as well, and if you look on the very bottom there, after 300 measurements, it was giving a mean rise time of about 4.02 nanoseconds, and if we put that number into the calculation, it gives us an answer of 266.8 megahertz. Blimey, that's quick. Yeah, and I've put an exclamation mark there because that clearly isn't right. And what's going on then? Well, I think what's going on is actually pretty straightforward. If we look at the specification, I've got another snip here from the spec for the oscilloscope. It says the rise time of the scope is typically 3.5 nanoseconds, so it's only 0.3 nanoseconds different to the rise time of the signal generator. And what I suspect is going on here is the Siglent scope needs a more challenging square wave to give you a meaningful result. And this is where the Schmidt trigger oscillator comes in, because Alan Walk, W2AW, in his video, which I linked to earlier, suggests the Schmidt trigger oscillator that I'm using has a rise time of about 2 nanoseconds, which hopefully will give us some more sensible results. So let's move on and look at those results then. I'm going to start with the Hantec DSO 5102P, which is specified as a 100 megahertz scope, and when we put the Schmidt trigger oscillator onto that, we get a rise time of 4.2 nanoseconds, which gives us a calculated bandwidth of 94.7 megahertz, which isn't terribly far away from its specified bandwidth of 100 megahertz. I think that's pretty respectable, really. The tablet scope, I reckon the rise time's about 10 nanoseconds. Maybe it's a little bit more than that, but let's be kind to it and call it 10 nanoseconds. If we plug that into the calculation, it gives us 35.7 megahertz, and as I said earlier, it's a 100 megahertz scope, so that's particularly disappointing, but I don't think it'll come as a surprise to those of you who are familiar with it. Now, I also thought it might be worthwhile doing the DSO 138 Mini, which if you're not familiar, that's a scope that you can build from a kit. It runs using a little microcontroller oscilloscope, but it is nonetheless something you can build, and it's quite a low spec. It does actually work. So quite difficult to measure the rise time, because the fastest time base is at 10 microseconds per division, and I've sat for a bit and decided that I reckon the rise time is about 3 microseconds. So putting those numbers into the calculation gives us about 116 kilohertz as a calculated bandwidth, and the specified bandwidth is about 200 kilohertz. And I wouldn't argue too much with that, because you could probably say that my estimation of 3 microseconds is extremely isn't very sound, and I wouldn't argue too much with that. So I think 116 kilohertz is probably being a little bit unkind to it. The Siglent gives us a rise time of 3.72 nanoseconds on the bottom line there, after just over 300 measurements, and if we put that in, we get a bandwidth calculated of 111.5 megahertz. It's a 100 megahertz scope, and yeah, as you can see, using a much faster pulse with a 2 nanosecond rise time has given us a much more meaningful answer for the Siglent scope. It isn't 200 and something megahertz at all, it's about 111, which is a number I'm in and feel a bit more comfortable with. Now finally, I've also got a 1970s analog scope. It's a Hameg HM307, and unfortunately I couldn't get a meaningful measurement because of the way the edge is displayed. I just couldn't get a sensible measurement at the fastest time base, which is 500 nanoseconds per division, but I couldn't even get the wave to display at that. But what I did do was I had a look at the spec, and bandwidth specification for the scope, which is supposed to be 10 megahertz, and the rise time it says is approximately 35 nanoseconds. And if you put 35 nanoseconds into the calculation, it gives you 10.01 megahertz. And I've put that in green there because that isn't a measurement, that's just a calculation taken from the specification. But I think that lends hopefully a little bit more credibility to the 2 nanosecond rise time that Alan Walk suggests is what we're getting from the Schmidt trigger. And of course, all of this is based on that 2 nanoseconds. That's not something I can actually measure, I'm afraid. However, I think those results speak for themselves. It is disappointing sometimes to see a scope specified as 100 megahertz when it clearly isn't, by quite a long way. And I think most of you have been perhaps looking at the reviews of that scope are fully aware that's the case. I think what is encouraging though is the Hameg, the DSO 5102P, which again is a budget scope. Mine cost me about £175 and it was coming up with a very reasonable 94.7 megahertz. So yeah, I reckon that's alright. So there you go, there are the results. Well, there you have it. The results, I guess, as I've said just now, speak for themselves in one way. Doesn't come as much of a surprise that some of the poor performance is what it is. I sort of expect that. Very pleased to see the Siglent performance actually exceeds its spec, and very pleasantly surprised to see how good the Hameg DSO 5102P has come out as well. So I hope that's been useful and might give you a little bit more information if you're thinking of getting one of these things. And for me, I think the irony is that particularly in the case of the tablet scope, if they just said it was 35 megahertz, I don't think people would have too much of a problem, but you just know that it isn't anything like that. Anyway, it is what it is, and nothing I can do about that. Thanks very much for watching. It'd be great if you could click the thumbs up. I hope you've enjoyed the video. Please let people know about the channel, and it'd be great if you could subscribe as well, and we'll see you on the next one.